All right, so let's look at an example. So we're asked here to compute a product of two matrices, A and B, and we're given A as a 2 by 2 matrix and B as a 2 by 3 matrix. Okay, so what we're going to do is we're going to look at B as a row of columns. And each of these three columns we're going to multiply by the matrix A. So we're going to start by first multiplying A by the first column of B, which is 3, 1. Okay, and the definition of that product is, well, we're going to go 3 times the first column of A plus 1 times the second column of A. So if you work that out, you're going to get 12, 3 plus 7, negative 2. So that gives you finally the column 19 and 1. So there we go. We're one column done. We just need to figure out two more columns, and then we have our product. So now we're going to multiply A by the second column of B, which is the column 4, 5. Okay, so how does that work? We're going to have 4 times the first column of A plus 5 times the second column of A. Oop, nope, that's not the second column of A. We want 7, negative 2, the second column of A. Okay, so that'll give us 16, 4 plus 35, negative 10. Okay, so now we'll put those together and add those together, and we get 51, negative 6. And so that's our second column of the product. Okay, and then finally we're going to multiply A by the third column of B, which is negative 2, 3. So we're going to have negative 2 times the first column of A plus 3 times the second column of A. So that works out to what? Negative 8, negative 2 plus 21, negative 6. So what does that give us? We'll have positive 13 and negative 8, and now we have everything we need. So we can finally say that the product of A and B is going to be, the first column is 19, 1. That's this one up here. Then our second column is 51, negative 6. And our third column is 13, negative 8. And notice that the result here is 2 by 3. Our product was a 2 by 3 matrix. And that can be, you can figure that out just by looking at the dimensions of your product. And you can do it by drawing what I like to refer to this as the dimension diagram. So start by just writing down the matrix A. You don't have to actually write out the whole matrix, just write the label and write out its dimensions. So we've got a 2 by 2 matrix. And then look at the matrix B, which is a 2 by 3 matrix. So now what you do, I shall use yellow. You look at the two inner numbers and make sure that they are the same, right? That's the number of columns of A and the number of rows of B. Those two numbers need to agree. That was really what we mentioned up here. A has to be M by N and B has to be N by P. So the number of rows of B and the number of columns of A has to be the same. And in this case it was, and that's why we were able to compute the product of these two matrices. But then these two outer numbers, the 2 and the 3, if I pull them down, that's going to give us, well, it's a 2 by 3 result. So take those two outer numbers and they will determine the dimensions of your product. So let me just add one last annotation here. So this is the dimensions of the product. So if you ever hear me say draw the dimension diagram, I'm referring to this here. Just draw this picture. So I guess it's not really a picture, it's just what you use to determine two things. First of all, is the product defined? Because if these two numbers don't agree, you would just stop and you don't even need to draw the rest of the picture because the product is not even defined. But if they are, then you can draw the rest to figure out the product, or pardon me, figure out the dimension of the product. Okay, now that's one way to compute products. That's actually, turns out, that's not the only way to define matrix products. You can define them one entry at a time using the following formula and use that to come up with a definition for matrix multiplication. And it will give you the same thing. So let's go through it. Because some people prefer this definition actually, and if not, it's still handy to have access to both. So you'd start with the same circumstances, right? You got to have two matrices, and the number of columns of the first factor A has to be the number of rows of the second factor B. And if you, under those circumstances, you can define the product just using the following formula. Okay, and this, when you first see this formula, it looks a little bit intimidating. There's an awful lot going on, and then it looks like there's an unknown number of terms. You get a term here, and then there's some terms in between, and then you got a final term. Okay, so what's happening here? Notice that you've got AI1 multiplied by B1K. Okay, well, what's the next term? You've got AI2 multiplied by B2K. So the I and the K stay the same, but it's the one that, the two occurrences of 1 here change to a 2 here. And then in the next term, you'd have AI3 multiplied by B3K, and so on, all the way up to the very last one, where you have AIN and BNK. So the first index on the matrix A is always an I, and the second index on the B is always a K. What you're really doing is you're accessing entries from the ith row of A and the kth row of B, and you're multiplying them, and you're adding up those products. And once you do that, then that gives you a formula for the entry in the product AB that happens to occupy the ith row in the kth column. So this works for a general I and a general K. So that's how we really have a formula for computing one entry at a time of the product. So but in practice, this is actually a lot easier than it looks. I promise you that. So let's take a look at this example. Okay, so we've got a matrix A and a matrix B. Let's start by just drawing the dimension diagram and make sure the product is actually defined. So we have, and then we can figure out what the dimensions will be for the product. So we've got A as a 2 by 3, and we've got B as a 3 by 4. So let's look, I'll just use the same color here. The two inner numbers are both equal to 3. So good, that means the product is defined. So the two outer numbers, the 2 and the 4, well, that tells us that the dimensions of the product A times B is going to be 2 by 4. So I'm going to just, down here, I'm going to write out some space just for, leave enough room for a 2 by 4 matrix. And we're going to compute the entries one by one. So for the first couple, I'm going to use some highlighting just to make it a little easier to pick up on exactly what's happening. So let's say I want to compute the entry that goes right here. So the entry that's in the first row of AB and is in the first column of AB. So the way I'm going to do this, back in terms of this formula, that means take I equal to 1 and K equal to 1. Well, if you plug in I equals 1 and K equals 1 all the way over here, what you're going to get, and you should try it. Pause this video if you want, and just write this expression out. But everywhere you see an I, write 1, and everywhere you see a K, write 1. And then take a close look at what you have. And what you'll see, and don't take my word for it, please actually pause this video and try it. But what you'll see is that you're actually just taking these entries and these entries, and you're just pairing them off in products. Like the 1 and the 4 are getting multiplied. Then the 2 and the 0 are getting multiplied. And then the 4 and the 2 are getting multiplied. And then you're adding up those products, and then the result is going to be the number that you put right here. So let's actually try it. We'll write it out carefully. So the product of AB, and we want the entry in the first row and the first column. So that is going to be 1 times 4 plus 2 times 0 plus 4 times 2. And, well, work that out and see what you get. You're going to get 4 plus 0 plus 8. You're going to end up getting 12. So this entry here is 12. So see how we did? We computed just that one entry and nothing else. So how do we get the rest of the product? Well, we do this 7 more times. We do this for each of the other entries. So let's do a different one. And this is the only other one I'll do highlighting for, because if I highlight too much, then the highlighting will all just kind of converge and conflict with each other and make it hard to read. So let's take these. Actually, let me back up. I shouldn't start with that. I should start with this. Let's figure out the entry down here. The one that occupies the second row and the third column of the product AB. So you're going to take the second row of A and the third column of B. And you'll repeat this process, and that will give you the entry in the product of A and B that's in the second row and the third column. So, well, let's see what this gives us. We're going to have 2 times 4 plus 6 times 3 plus 0 times 5. That's a multiplication in there, just to be clear. Okay, so 2 times 4 is 8, 6 times 3 is 18, and 5 times 0 is 0. So we're going to have 8 plus 16 is 26. So that means we have a 26 in this position. And you just keep going in this fashion. One by one, you can compute all the entries. So let's do that systematically. So let's go A, B, 1, 2. So first row, second column. So we're talking about the entry that goes here. So we're going to do the first row of A is 1, 2, 4, and the second column of B is 1, negative 1, 7. So we're going to have 1 times 1 plus 2 times negative 1 plus 4 times 7. So we've got 1 minus 2 plus 28. So that's going to give us 27. So we're going to put a 27 here. And then for the next entry in that row, we'll have AB 1, 3. So that'll be the first row of A and the third column of B. So we'll have 1 times 4 plus 2 times 3 plus 4 times 5. Okay, so we've got 4 plus 6 plus 20. So that's going to give us 30. So we have a 30 there. Last one in that row, AB 1, 4. We're going to have first row of A, fourth column of B. So we've got 1 times 3 plus 2 times 1 plus 4 times 2. Okay, so what happens? We get 3 plus 2 plus 8. So that's going to be 13. So we'll have a 13 as the final entry in the first row, and then now we can finish off our second row. So AB 2, 1. So second row, first column, we're talking about this entry. So we're going to take the second row of A and the first column of B. So we're going to have 2 times 4 plus 6 times 0 plus 0 times 2, and that works out to 8. 8 plus 0 plus 0. So we've got an 8 in that position. Okay, what about the next one in that second row? So A, B, 2, 2. So we want second row of B, second row of A, second column of B. So we have 2 times 1 plus 6 times negative 1 plus 0 times 7. So we've got 2 minus 6, which is negative 4. Okay, one entry to go. We'll have to compute the entry in AB that's in the second row and the fourth column. So we want second row of A, fourth column of B. So we're going to have 2 times 3 plus 6 times 1 plus 0 times 2 finally. And that's going to be 6 plus 6 plus 0. So finally, we have a 12 in that last position, and that is our product. So that's how you can compute the product one entry at a time. This second method is particularly helpful because there may be certain situations where you only need to compute a particular entry of a product. You might not need to know every other single entry. So the first method, you have to compute entire columns, right? We had to compute an entire column at a time. Then the second column, and then the third column. So this definition, I mean, if you're computing the whole matrix, there's nothing wrong with this method. In fact, I wouldn't actually want to even say which one's better. But if you only want to compute one or maybe a handful of entries and you don't need to compute the whole product, then this method would be superior in that case. But it's good to be familiar with both of them.